Hola. Alguien se...
Pero por el otro.
No, está bien, perfecto. Bueno, okay, so hi everybody. Welcome to a new edition of the Chilean Probability Seminar after like 2 weeks, maybe, or 3 without a seminar. So today I have the pleasure of introducing Manuel Cabezas. He's a professor here at PUC, who's going to talk to us about random walks on lattice trees. So, todo, Manuel.
¿Y hablo en inglés o en español?
No, en inglés.
Okay, so what I'm going to talk about is joint work with Gérard Ben Arous, Alexander Fribergh on one side, and on the other side with Holmes and Ed Perkins. Okay, so this is my collaborators on this project. So Okay, so I'm going to start by giving some simpler models of random trees. So first of all, what is a tree? A tree is a graph which doesn't have any cycle. So it's a graph tree. Okay, and I'm going to consider as the simplest model. I don't know if it's the simplest, but one of the simplest model, or at least the best known models of lattice of random trees is the branching processes. So you take one particle, and this particle has some offspring according to some probability distribution, and then each one of the offspring has in turns has another offspring with the same probability distribution, and then you create a genealogical tree in this manner. And this is a random tree, a very, very well-known random tree. And this tree has a phase transition in terms of one parameter. The parameter is the expected number of the number of children, and if the expected number of children is bigger than 1, then you will have survival forever with positive probability. And if it is smaller than 1 or equal than 1, then the process will be extinct almost sure. Okay. So another way of considering a random tree is just consider a uniform tree in some set. Okay, so this is another way of considering a random tree. So how we do this in this case? One way of doing this in this case is to consider fixed n, the fixed number n, and you consider all the possible trees which have n vertices, and I'm going to consider labeled vertices. So vertices labeled from 1 to n, you label vertices from 1 to n, and then you consider all the possible different trees that you have. And then you take one uniformly at random. Okay? This is another model of taking, of producing a uniform tree, but actually it's not another model, it's the same model, because if you do this, it is exactly the same as taking a Galton-Watson process, a branching process, whose offspring is Poisson of parameter 1. So you take a Poisson of parameter 1, and then you condition this genealogical tree on having exactly n vertices. And what you get is exactly the same as before, as taking this uniform tree on all the possible labeled trees in n vertices, if you disregard the labels afterwards. Okay. So there is a further model. Now this is a little bit more interesting. So you will take n vertices. Okay, you take n vertices, again labeled vertices from 1 to n, and you choose the vertex 1 as the root. And then for each number from 2 to n, what you do is you take the vertex with label I, and then you connect it with the vertex of label UI, the minimum between UI and I minus 1, where UI are uniform random variables in the set 2 to n. So essentially, maybe I'm going to try to make a drawing. So hopefully you see. You start with the vertex label 1, okay? And now what happens with the vertex label 2? The vertex label 2 will have to connect with the vertex label 1 because it doesn't have any other choice. So in this case, the minimum between UI and y minus 1, so y minus 1 will be just 1. So the minimum will be 1. And there's no other choice. There's no other choice. And then you will have a connection. So now what happens with vertex 3? So the vertex label 3 can either connect with the vertex label 2, or in the very unlikely case that the U3 random variable is exactly 1, then it can connect also to 1. But most probably it will connect to 2. I mean, with much larger probability, it will connect to 2. So it will be this way. And again, the vertex label 4 will also most likely, if n is large, connect with the vertex 3. Okay. But at some point, let's suppose that this point is 5, at some point, the UI will be smaller than I minus 1 with a certain probability. And in this case, the new vertex, so let's say the vertex 5, for instance, so let's say that U5 is 3, or better, let's say that U5 is 2. If U5 is 2, then this new vertex will connect to this one, okay? And then probably, again, the vertex labeled by 6 will be here. Okay. And 7, and at some, what I'm meaning is that this thing grows like a line, except by some exceptional times, let's say, where this vertex labels to a vertex which was already on the tree. Okay, and you construct the tree in this way. And the thing is that again, this is not a model; it's the same model. If you do this and you finish the construction, you reach up to vertex 2, you have the same law as the models described before. So in particular, as the uniform label tree on n vertices. Okay. So while I'm describing these models, I want you to pay attention in this construction, in the construction of adding vertices one by one. In this construction, when I'm adding a vertex at a location which is not the next, which is not the leaf, a leaf on the tree, I am attaching at a new point, and this new point is uniform on the structure that I already have. Okay, I think that my drawing doesn't show, but okay. This is the idea. Okay. So all these three models of trees have the same law in the end. So are there any questions so far? No. Okay. So if you have any question, please just raise your hand or just
Manuel?
Talk. Yes.
Just you said that in general you are going to grow linearly, like in a line, but it's,
yeah.
At least for me, it seems that when you are moving forward in time, at some point become more probable to get connected to someone in the past, not the previous one.
Yeah, right. So in the beginning, you start with a line, you start growing a line, then this line becomes a Y shape, you start to grow, but then when n is very large, you're almost, you're right. Yeah. When n is very large, you are attaching to previous points more likely. Yeah, that's right.
Okay, thank you.
But you start growing a line. You start growing a line, then you do a Y shape for a long time, and then in the end, it's more and more likely to connect to the past. Okay. And now, so I will be interested in asymptotic behavior as the number of vertices of the tree is large. So what I'm going to consider, for instance, to fix ideas, is Tn, the genealogical tree of a critical branching process with finite variance in the offspring distribution. This is more, you can say it's technical. And so I'm going to condition to have n vertices. Okay, so I have a large tree, large genealogical tree on n vertices. And then what I'm going to do is to rescale the edges in a certain way in order to obtain a non-trivial limit. Okay, so what it turns out that the right scaling is square root of n. It turns out that the right scaling for this object is square root of n. And when n is very large, these things converges to something. Okay, this something is a random real tree, and it's called the continuum random tree. And it has many properties, many nice properties. But I'm not going to be focused here exactly on the continuum random tree. You can, during this talk, you can think of the continuum random tree just as the limit of branching process when they have a large number of vertices. Okay. So this is the continuum random tree. And another notion that I will be using during the talk is the notion of skeleton. So you have your large genealogical tree of a branching process, and n is very large, and fixed k, so k will be a fixed number, which will not diverge with n, and you take k points, k vertices of your tree uniformly at random and independent. Okay, so now you have k vertices on your tree, and with these k vertices on your tree, what you do is to consider the subtree spanned by these k vertices. Okay, so in the end, the skeleton, even though your tree is very large and has a very large number of vertices, yes. Better if I write here.
I can change the.
Okay.
Let's see if it works.
I don't think it shows too much.
You right there, put more light. It's not too bad.
Okay, so I'm going to try to not write too much anyways. Even though your tree is very large, you can your K skeleton will be something that will most likely have K leaves. Okay, so in this case, K is 1, 2, 3, 4, 5, and and will be like in some sense like a finite dimensional object. Okay, so. Okay, you guys probably already saw it. Okay. And many of the properties of the tree or the convergence of the tree can be stated as or can be studied through these skeletons. Okay, so these skeletons play the role as the finite dimensional distribution, for instance, of a random process. If you have a random process, just study the finite dimensional distribution, and you can do a lot with it. If you are studying random trees, you study the K skeletons, and the K skeletons correspond, in some sense, play the role of finite dimensional distribution. Okay, so you can also consider the K skeleton of the continuum random tree. Okay. So the continuum random tree, recall that it's the limit of Galton-Watson tree when they have a very large number of vertices. What you do is that this tree comes equipped with a metric and also with a I'm not going to explain this, but it's naturally equipped with a measure. And since it's naturally equipped with a measure, it is actually a probability measure. Okay, so you have a probability measure on your tree. You can span points uniformly at random according to this measure. And you span k points uniformly at random according to this measure. And then you construct the subtree spanned by these k points. And this is called the k-skeleton of the continuum random tree. Okay, so in general, you can almost so there is a way of proving convergence of random trees to the continuum random tree, and one of the main ingredients is to prove that the k-skeletons converge to the k-skeletons, and these k-skeletons are in some sense finite dimensional objects. They are described through a finite number of parameters. Okay, so this is the nice thing about the k-skeleton. They have a shape, and this shape also have some lengths. But once you have this shape and this length, this is just a finite number of parameters that completely describe your k-skeleton. And this is why they are important. Okay, so I am going to also give a different construction of the k-skeleton. Okay, so now what you can do is you're going to consider a Poisson point process on the real line, not on the real line, on the positive real line. Okay, and you consider an inhomogeneous Poisson point process on the line. So the intensity of the Poisson point process will be t dt. So the intensity is increasing. You are increasing the intensity with time, in some sense. And then you will have marks. So the marks will be more and more, there will be more and more marks as you move when t is large. Now you enumerate the marks as x1, x2, x3, and you enumerate, and not only enumerate, but order them, okay? So now what we're going to do, we are going to take a scissor and cut the line on these marks. So now I have an infinite number of line segments. Okay. So when I have this, what I'm going to do is take the first line segment. The first line segment is just 0, x1. And then when I have this line segment, then I'm going to take the second line segment, which is from x1 to x2, and I'm going to glue these two things. So the way I'm going to glue it is by identifying the edge x1 at a uniform point in the line 0, x1. Okay, so I'm gluing it at a uniform point. And then I do this for each k. So once I have constructed the tree, which I call here jk minus 1, in this fashion, I just glue the interval xk minus 1 xk to a uniform point in the tree jk, and I get another tree. Sorry, and I glue it to a uniform point in jk minus 1, and I obtain another tree. Okay. The nice thing, probably surprising thing, is that jk is exactly the same thing as tk, as the k-skeleton. It's another way of constructing the skeleton of the continuum random tree. So it's a way of constructing the skeleton of the continuum random tree without using the continuum random tree. You just take a line and cut points and so on. Okay, so one thing which is probably important to see here is that, okay, the thing that I'm going to recall in the future is that when I'm gluing a point at a uniform position. So this is important, okay? So the new point comes attached at a uniform position of the previous skeleton. And also, the second part, which is probably important also, is that the length of the trees diverge, because this uniform point process doesn't have any accumulation point. By the intensity is T, you can show this with probability 1, this post-1 point process doesn't have any accumulation points. So actually, the union of all these line segments xk minus 1 comma xk is the whole line. Okay. Okay, so these are some things about abstract trees. So I'm not going to consider abstract trees. I'm going to move now to trees which are embedded on CD. And the main model of the talk, which is the model of lattice trees. Okay, so what is a lattice tree? So it's the name. It's a lattice tree. It's a tree on the lattice. You take a subgraph of CD, which is a tree. Essentially, this is a lattice tree. A subgraph of CD that doesn't have any circles, and also we are going to ask that it's finite, that it's connected, and that it contains the origin. So once I have this set of lattice tree, I'm going to give a weight to each lattice tree in particular. So the weight will depend on a parameter p, very much as percolation, and the weight of a tree is just p to the power the number of edges of the tree. Okay, so there is a phase transition also here in terms of p, so that there is a critical value such that at the critical value, the constant rho there, which you will see is just the total weight of all the trees, is finite. But the expected size of a tree is infinite, where I am taking expectation with respect to the measure that these weights give. So since these weights are, the total sum of the weights is finite, they define a finite measure. I can normalize this finite measure just by multiplying by rho to the minus 1. Now this is a probability measure, and now I can take expectation with respect to this probability measure. And at this value, the expected size of a tree is infinite. So this is the critical value. Okay, so this is the definition of lattice trees, but what I'm going to do from now on is to consider lattice trees conditioned on have exactly n vertices. And the important thing is that if you condition a lattice tree to have exactly n vertices, what you get is a uniform tree. So you take all the subtrees of CD that have n vertices that contain the origin and that are connected, then you take one of these uniformly at random, and this is a lattice tree condition having n vertices. This is just because any two trees with the same number of edges will have the same probability by the definition of the weight. Okay, so in some sense, this is the definition of lattice tree, but I could have just told you that I'm going to consider the set of subtrees of CD that contains the origin, are connected, and have n edges, and I'm going to take one of these uniformly at random. Here's a picture of a lattice tree. This is a nearest neighbor lattice tree in C2. Any questions so far? No. Okay. So, so what are the possible? So I talked about of the branching processes, the genealogical tree of a branching process. So what is the possible scaling limit? Not only the possible, but what is the scaling limit of a lattice tree? So what we need, so it is going to be a random tree, a random real tree, but it will be a random real tree which lives on RD, right? It has a geometric component to it. So as the lattice trees are embedded in some way on CD, this random tree will be embedded in some fashion also on RD. So, so this object that we will obtain will be called the integrated Super Brownian excursion. So it's a long name, but okay, it's not. I think it's not so complicated. So you take the continuum random tree, okay, which is the limit of the genealogical trees of branching processes, and now you fix your tree. You fix a realization of the continuum random tree, and you're going to take a function, and this function is random itself, and this function goes from the tree to RD. So you are going to put this tree on RD in some way. So what does this tree does? So maybe here again, I'm going to use a little bit of the whiteboard. So if I have that is very simple drawing, so it doesn't matter. If I have here the root of my tree and some vertex V of the continuum random tree, so here the continuum random tree has a lot of more things going on here, but I'm concerned about the image of the geodesic between the root and V, and this will be mapped to a Brownian path, okay? To a Brownian path on RD. And the other property is once, if I now consider two different geodesic, after the branching point of the geodesic, the key embeddings will be independent. So when the geodesic are the same, they are mapped to the same Brownian path, but once they branch, they are mapped to independent Brownian paths. Okay, so in some ways, map each line to a Brownian path. And what is the integrated Super Brownian excursion is just the continuum random tree together with this embedding. Okay, so you consider the continuum random tree together with this embedding, and you get an object, and this object is called the integrated Super Brownian excursion. And this object is the scaling limit for the lattice trees. Okay, so I'm going to explain this in a little bit more of detail.
Yeah. What's the relationship between the integrated Super Brownian excursion and Super Brownian motion?
Yeah, so they are super related. So actually they are the same. Okay, so but I don't know if some of you have heard about Super Brownian motion. The Super Brownian motion is a measured valued random process. And this thing is just a random tree in some sense, together with an embedding. But it's the same object if you look, so it's the same object looked from different perspectives, okay? So this thing doesn't depend on time, it doesn't have time, it doesn't, so that's why it's called integrated, because it's integrated in time. It's not a process, just an object. And so the relation is more or less as follows. Take the integrated Super Brownian excursion. Take all the points in the continuum random tree that are at distance t from the origin. Okay? So now take the image of these points by this function, and it will give you a set. Mm-hmm. So in some sense, this set is not exactly a set, it should be a measure, but it's a measure also. It's a measure that depends on time. You have a measure on RD that depends on time. If you consider this measure that varies in time, you have a measured value process, and this is the Super Brownian motion. So how do you get the measure? Let me try to explain this a little bit better. So as I told you, the continuum random tree comes with a measure, with a total measure, but also you can decompose this measure according to the levels. So you have for each level t, for each level, it means the set of points that are at distance t from the root. You have a measure, let's call it lambda t, that depends on t and is concentrated on the points at distance t from the root. It's called a local time measure also. And the image under this function phi of this measure gives a measure on RD. And then you have the Super Brownian motion. So it's, if you know the Super Brownian motion, this object is the same as Super Brownian motion, just I'm looking at it in a different way. I'm not looking at it as a measured value process. Okay. So what's the main theorem? And here I should say all the people involved I'm going to say that the scaling limit of lattice trees is the Super Brownian motion, but this is a lot of theorems in some way, different theorems that are being improving in time. So Derves and Slade, Van der Hofstadt, Holmes, Perkins, all these people are involved in this development. So what you do is that essentially for dimension bigger or equal than 8, the scaling limit of lattice trees is the integrated Super Brownian excursion. Okay, I'm going to put it like this, just more briefly probably. So why? So this is important. Why the dimension should be larger than 8? Okay, there is at least one good reason for this, for why the dimension should be larger than 8. The mapping phi that maps the continuum random tree onto RD is only injective when the dimension is larger than 8, larger or equal than 8. In dimension smaller than 8, this mapping is not injective. So actually, the image of the tree under this mapping will not be a tree. So this is at least one of the reasons why this theorem should only hold for sufficiently large dimension, and the right dimension is 8. For dimensions smaller than 8, this is probably not true. Okay, it's probably not true that the scaling limit of lattice trees is the integrated Super Brownian excursion. So what we are going to do here is for the rest of the talk, I'm working on the high dimensional setting where this theorem holds. Okay. Okay, so I am not only concerned about scaling limits of trees, but I am concerned about scaling limits of random walks on trees. Okay. So let's go to the basics. Let's forget a little bit about the continuum random tree and talk about let's forget about the lattice trees and talk about genealogical trees associated to branching processes. So Tn is a genealogical tree of a branching process conditioned on having n vertices, and we are going to consider a process xn, which is just a simple random walk on this tree. Okay, and David Croydon has shown that this process converges to something which is called the Brownian motion on the continuum random tree. So it turns out that because the continuum random tree is a tree, you can apply the theory of resistance forms. Okay, so it's kind of an analytical tool that you can use to show and to construct the Brownian motion on this object. So it's a Brownian motion on a fractal. Actually, the continuum random tree is a fractal. You can define the Brownian motion on the continuum random tree. And something that David Croydon showed is that if you rescale the random walk appropriately, it converges to the Brownian motion on the continuum random tree. Okay. So we are going to call the Brownian motion on the continuum random tree B superscript T. Okay, so it's a process that is indexed by time and takes values on the tree T. Okay, so now what happens with random walks on lattice trees, which is the main theorem, what I am going to try to explain now. First of all, we will need something as the candidate for the scaling limit. So the candidate for the scaling limit will be the Brownian motion in the integrated Super Brownian excursion, okay? So there are several ways of defining this object, but I'm going with the simplest possible way. So I'm just going to say that this object is, you take the Brownian motion on the continuum random tree, and you apply the function that takes the continuum random tree onto RD, applied to this process. And you have a new process, which is phi of B. Phi of B is the Brownian motion on the integrated Super Brownian excursion. Okay? But this is, again, this is only true, this way of writing the Brownian motion on the integrated Super Brownian excursion is only true when the dimension is larger or equal than 8. So when I know that this function is injective with probability 1. Okay. If this function is not injective, then the image of the continuum random tree under phi will not be necessarily a tree. Actually, it will not be a tree. We will have cycles. And actually, it's an open problem actually to define the Brownian motion in this subject, because since it's not a tree, I cannot apply the techniques of resistance forms to show that, to construct and actually to define the Brownian motion on this tree. So here is a very nice, if you want, very nice problem. If you want, define the Brownian motion on the integrated Super Brownian excursion for dimensions, I don't know, 6 or 7, something like that. Okay, but forget about that. Let's say that Yn is a random walk on a lattice tree, and it is conditioned to have, so that when the lattice tree is conditioned to have exactly n vertices, and the main theorem that I want to address in this talk is that if you rescale these random walks, this sequence of processes converges to the Brownian motion on the integrated Super Brownian excursion. Okay, so this is the...
And the scaling is different from before, right?
Yeah. Nice question. So the scaling is different. So I think we have time, so I'm going to explain a little bit the scaling here. So here the scaling of space is n to the minus 1/4, and then I'm going to explain the scaling of time. So let's compare, let's go back here. So let's compare with the theorem of Croydon, with the theorem of convergence for the case of random walks on genealogical trees of branching processes. In this case, so I'm going with Croydon first to explain the exponents. In this case, the exponent is n to the minus 1/2, the spatial scaling. Okay, so it means that xn is more or less of size n to the 1/2. So why is this true? It's simply true because the lattice, the Galton, the genealogical tree has diameter n to the 1/2. So if you take a lattice tree that has size, has total number of vertices n, the diameter of this tree with the intrinsic metric, with the graph metric, will be n to the 1/2. Okay, so I'm going to make that the random walk explore the whole tree. I'm going to give it time to explore the whole tree, and since it's exploring the whole tree, it will be of order n to the 1/2. So now, how much time do I have to give this random walk to explore the whole tree on this completely different subject? I have to give it n to the 3/2 time. So how can I explain this? Okay, I can explain this if you know the commute time formula. So this is the fastest way. The commute time formula says that if you have a random walk, a reversible random walk in any graph, essentially, the commute time between 2 points, so the commute time is the time that it takes, the expected time that it takes from going to x to y and then going from y to x. So that's why it's commute, going back and forth between two vertices. The commute time is exactly equal to 2 times the effective resistance between x and y multiplied by the edge volume of the graph. Okay, this is very well known. I mean, it's not too standard, but it's something which is very well known. Commute time formula, random walks on graphs in general. So, okay, what is the effective resistance? The effective resistance is actually the electrical resistance. It's just you consider your graph as it is, as if it were an electrical network. You put unit resistance on each edge, and then you compute the resistance between 2 points. Okay. In this case, if you take 2 points which are far away, it doesn't matter if they're far away or close. The resistance will always be the distance between the points, because it is a tree, and in a tree it's like computing resistance in series. Okay, so the resistance between 2 points, just the graph distance between the 2 points. If I take 2 points which are a macroscopic resistance on the tree, the resistance will be of order n to the 1/2, just because the points are a distance n to the 1/2. Okay. The edge cardinality is the vertex cardinality -1, which I cited it's n. So it's n minus 1. So it will be square root of n multiplied by n. So n to the 3/2. So the commute time is n of 3/2. So this is an explanation that says that this is the amount of time that you have to run your process. Okay. Now let's go to the case of lattice trees. In the case of lattice trees, you again are conditioning on having a tree on n vertices, and something which underlies all this problematic is that when the dimension is large and the tree is, when the dimension is large, larger or equal than 8, and the number of vertices are very large, the continuum, the lattice tree very much resembles a genealogical process of the genealogical tree of a branching process. So it means that the resistance will also be, I mean, the graph distance between 2 points will be also of order n to the 1/2. So what I'm meaning is that the diameter in the intrinsic distance is of order n to the 1/2, and also again the number of edges will be n minus 1. So this is why I have to rescale the time by n to the 3/2 again. But why I have n to the -1/4 in front instead of n to the -1/2 is now because the graph distance of my tree, the graph diameter of my tree will be of order n to the 1/2. But then this graph distance is embedded in some fashion on CD. And the way it is embedded, and this has to be explained and so on, but the philosophy behind it is that the way it is embedded, it looks like a random walk, like a simple random walk. Actually, it has to be a self-avoiding random walk because it cannot have loops, but it's more or less like a random walk. And so if you take a random walk that gives n to the 1/2 steps, so what's the distance on CD? The distance is n to the 1/2 to the 1/2, so n to the 1/4. This is why the diameter of your tree now in CD is n to the 1/4. So lattice tree have two different diameters. Diameters in the intrinsic metric, which is n to the 1/2, and diameters on the extrinsic metric on CD, which is n to the 1/4. Okay, so this is why you have these scalings. Okay, now what I'm going to do again is to consider the skeleton of a lattice tree, and I do the same thing. So I consider a lattice tree conditioned on have n vertices. I take k points sampled uniformly at random, and then I take the subtree spanned by these points and the root. Okay. Now the difference is that this skeleton will also be embedded on CD. So what are the conditions of the convergence of So okay, in a previous work with some co-authors, we worked in a general setting. So and we provided a set of conditions that if you show these conditions, then you show that the random walks on these graphs converge to the Brownian motion on the integrated Super Brownian excursion. Okay, so try to isolate these conditions. So essentially there are 3 conditions, but I'm going just to talk about 2 conditions here. Okay, I'm going to explain the 3rd condition, but it's going to be trivial in this case. So first of all, we have a geometric condition. So we in some sense want that the graphs looks like the integrated Super Brownian excursion. Because if we want that the random walks on our graphs looks like the Brownian motion on the integrated Super Brownian excursion, we of course need that the graphs looks like the integrated Super Brownian excursion. So we want that a process on these graphs look like a process in this other object. We need, first of all, that the graphs looks like this object. And this will be the geometric convergence. So let me call B of Tn the graph metric on Tn. So recall that Tn is a lattice tree condition on having n vertices. And the condition G is more or less the following. We take the pair, considering the graph scaled by n to the minus 1/4, with the intrinsic distance, with the intrinsic distances scaled by n to the minus 1/2, and this pair converges to the K-skeleton of the integrated Super Brownian excursion. So in some sense, more loosely speaking, what I'm saying is that the discrete skeletons converge to the continuous skeleton. Okay? The discrete skeleton converge to the continuous skeletons. And also, I will need something of different nature, which is convergence of volumes, okay? So here the volume will be related with, here the volume will be related with the random walk because of the following. So I am going to consider the volume given by the cardinality of the tree. Okay, so I'm going to project the cardinality of the tree onto the K-skeleton, and this is going to give me a measure. Okay, so I'm going to consider pi k sub n is the projection onto the skeleton. I can only always project a tree onto a subtree. And I'm going to consider mu n the cardinality measure on Tn. Actually, it's the edge cardinality, but it's not very different from the vertex cardinality. And then I'm going to project the measure, the cardinal measure onto the skeleton. And I'm going to construct mu nk. So mu nk is a measure on the skeleton. And condition V says that if k is large, the volumetric condition says that if k is large and n is large, then the measures mu and k are more or less uniformly distributed over the skeleton. Okay. So why do I need this? Why this is necessary? You can think, maybe thinking again on the commute time formula. So the edge cardinality of a graph controls how fast a random walk moves along this graph. So recall that I have 2 points. The commute time between these 2 points is just the resistance multiplied by the edge cardinal. So the edge cardinal controls how fast a random walk moves along this graph. So I want that my random walk moves along the skeleton more or less in a uniform speed. Okay, I don't want that my random walk move faster on one side of the skeleton and slower in another part of the skeleton. If this happens, then I won't have convergence to the Brownian motion on the continuum random tree. So this is more or less the reason that I need this edge volume to be uniformly distributed over the graph. There is a third condition that is in order to control the transition probabilities. This third condition is also that if I take a uniform point, the resistance is asymptotically proportional to the graph distance. But this condition only makes sense when my graphs are not trees, when they have bubbles. But since these graphs are trees, this is completely obvious, okay? And these resistance conditions is what controls the transition probabilities of a random walk. So the transition probabilities of a random walk comes controlled by the resistance, but this is trivial in the case of a lattice tree because it is a tree. And I only have to consider the geometric convergence, so condition G, and volumetric convergence, so condition B. Okay, so geometric convergence is...
Sorry, I have a question. So, but does that mean that your graph somehow needs to look like a tree with...
Yes.
Okay.
So for instance, I'm thinking about percolation in high dimensions. So in the large scale, it looks like a tree, but in the smaller scale, it isn't a tree. Okay. So that's why, in that case, the condition condition of the resistance will have some meaning. Here, it doesn't have any meaning. It's immediate. So, okay, very nice. I don't have to prove the linearity of the resistance. I just have to show these two other things. And the geometric convergence is a whole work. So we have a set of works with Mark Holmes and Ed Perkins and Alexander Fribergh, in which it turns out that we have to use Lake's expansion to prove historical measured value process convergence. So if there's something even nastier than measured value process convergence, yeah, it exists. It's historical measured value process convergence. And if you do this, you can use the tools typical of the field to improve the convergence and to get the geometric convergence. This is one article that we have submitted now. Actually, two different articles that we have, one of them published and the other submitted, in which essentially we prove condition G. Okay, now what about volumetric convergence? So now I'm going to be finished soon, yes? Yeah, I'm going to finish soon, yeah, okay. So it turns out that that in general, you can deduce condition B from condition G, okay? You can deduce condition B from condition G. This is something we found, we discovered after we have published these general conditions. So maybe if we have known this, we would have never write condition B, okay? But this is, okay, so the last nail on the coffin was to show this, that actually condition B also comes from 3 because it follows from condition G. So
Always?
You only need that the way of sampling the points is uniform or approximately uniform. Okay. So the challenge, as I write here, is to obtain an estimate on the whole of the tree, because you need that the volume is uniformly distributed. So you need to know whole of the tree to say something about the volume. But you want to use only finite dimensional information, because you want to only use information given by the skeleton. Okay, so the idea is the following. Maybe I'm going to pass to the next slide here. The bold line here is the tree TK. Okay, so it's the skeleton that I want to show that the volume is uniformly distributed on. Okay, so now I'm going to approximate my measure mu nk by a measure which I'm going to call mu hat n k k1 k2. Okay, so which only depends on the tree Tn k plus k1 plus k2. Okay, so in the skeleton with k plus k1 plus k2. So I have T and K, my K skeleton. And now, first of all, I'm going to choose atoms in this skeleton. So what I'm going to do to choose the atoms is the following. Here in this drawing, the bold line is the first tree, TK, and the thin line is the second tree, is Tn k plus k1. Okay, so as you see, I'm going to have a lot of dangling parts of my tree. Okay, so these dangling parts connect at some points in my tree Tnk, and these points of connection will be the location of the atoms. Okay, so now I fix k, I have a large number of atoms. So sorry, I fix k1 to have a large number of atoms in my tree. Okay, and then I choose k2 extra points where k2 is large, and I count how many of these k2 points lands on each of the parts of my tree tk1, sorry, tn k plus k1. And according to how many points of this land on each part, I'm going to assign weights. And the thing is that for k1 and k2 large enough, I can show that this is actually a good approximation of the whole measure mu n. But the nice thing is that this measure mu hat only depends on finite dimensional information. So by condition G, I can show that this measure converges to a continuous counterpart, which is mu hat k, k1, k2, which is doing the same, but in the continuum random tree instead. And then I can show, by the final step, I can show that this measure, mu hat k, k1, k2, is approximately uniformly distributed over the tree tk. And joining these three things, I can essentially prove the theorem. A little bit before I finish is just to say that while this measure mu k, k1, k2 is approximately uniformly distributed over tk, well, you have to, here I would like to make the connection with the fact that the line breaking construction. In the line breaking construction, each time you attach a new point, you attach a point uniformly distributed on the previous tree, and this is related with this. I don't have to time to explain this in detail, but you can show that. Okay, so this is all, and thanks.
Okay. So thank you, Manuel. Hi. So any questions maybe in the chat? Well, we'll wait for questions. So I have a question. So can you explain the last part with the K2 again? So how from the light tree, how do you attach?
Yeah, so you have this. So here the drawing is just for tk1 plus tk plus k1. The k2 is not being drawn yet.
Yeah.
Okay. So here I have some parts, the light parts, and I have these are different connected components. Different. And now if I sample more points, these are going to land on, well, they can land on the both part, but the probability of that will be very small. They will mostly land on the light parts because I choose K1 sufficiently large so that the light part is much larger. Okay? So many of them will land on this part. So how do I construct the measure? Now it's I just count how many of these extra K2 points land on each one of these connected components. And this will give me the weight of my new measure.
Okay. Any other questions? Well, no. So I have one more question. So this is for D larger or equal than 8, but also L has to be large enough.
Mm. Yeah. I should have eaten that cookie. Okay. So generally, on this kind of models, you have two choices or two types of theorems. You can either choose to consider a spread out model in which you add more edges. So now, instead of considering CD with nearest neighbor edges, I can consider CD with long edges, which joins any 2 points which are in a box of radius L. And this is called the spread out model. I can define the model in the spread out case just as good as I did. And if I do this, I can consider, and this is in general for most of the theorems on the field, I can consider the right dimension. So in this case would be dimension 8. It depends on the model though. And sufficiently spread out to prove the theorem. So in this case, I can either show that for the right dimension, so dimension 8 and above, but sufficiently spread out, then I have my results. Or the other thing that I can do is to stay nearest neighbor, but in that case, I have to choose D large enough. So I cannot reach to the real critical dimension.
But this is supposed to be D equals 8 for every
Yeah, it's supposed to be true for D equals 8 for nearest neighbor also. But it's the techniques of the proof doesn't allow to prove that actually.
Okay, I have one more question. So, like, what's the next step would be like the random walk on the percolation cluster, or
yeah,
that's where you're aiming to do?
Yeah, but that's, I mean, there are being advances recently, I think by Hutchcroft. We are doing things too. We are we are doing something which, okay, we are constructing the by infinite incipient infinite cluster. This is
working,
but we're still working. Okay, so what we want to do is construct an object which is the by infinite incipient infinite cluster in order to prove condition R. So we have a paper which is already finished with Antal Jaray, Marcus Heidenreich, and Alexander Fribergh. That is the existence of the two-arm IAC in high-dimensional percolation. But this is just one of the steps. There are many steps.
And like, which steps are missing? Like condition.
All of the steps are missing.
All of the steps.
So all of the steps are missing in percolation. Yeah. So I think I've heard that. I don't know if this is true, but probably I don't know. I have to check. But I heard that. So what's the status in percolation? This percolation is not proven that percolation converges to the Super Brownian excursion, not only the graph part. And I think this is being, there are advances in that direction now.
Okay. So if there are no more questions, then we thank Manuel again. And